free to speak a little bit about your interests, and we want to keep it informal.
Absolutely. All right. Thanks so much, Madhura. Thanks again for the invitation. I remember this is again the time of the year, or this was the time of the year last year when we were doing our previous summer school. That way it's good because I get to reuse a lot of my slides from last year. Hi everyone, my name's Manu Awasthi. I'm a faculty member in computer science at Ashoka University. I mostly work in computer architecture. My bread and butter research for the past, I don't know, 15 years or so has been around memory and storage systems. Storage systems for the second half of it, but memory systems, which includes caches, on-chip memory, non-volatile memory systems for the past 15 years or so. I started out on caches, moved to memories, then kind of moved to storage, and now I work in this entire space, trying to pick up problems that seem interesting. And then there are a lot of interesting problems in this domain. So I'll keep this short. What I have is a bunch of slides, which are mostly introductory slides on use of non-volatile memory and a bit about I/O systems. And I know I only have an hour and 15 minutes, so I'll try to give you a high-level introduction of both non-volatile memories as well as storage subsystems. I have around 50-ish slides, but I don't have to cover all of them. What I really want to do is essentially have, or just to convey to you some sense of how important this particular subsystem in the computer system design is, and how it is going to be one of the crucial subsystems that would need to be optimized, especially in this age of big data and whatnot. Right. So again, just to quickly start out here, what I'll do is I'll talk a little bit about. I'll start out with non-volatile memory subsystems and then move on to storage subsystems. But as I said, I don't have to cover everything. Please feel free to interrupt whenever you think you don't understand something or you might have questions. We don't necessarily need to stick to the slides. We can just digress and have a discussion in this general area. And I'll be available during afternoon as well during for the labs as well as for the doubt clearing session later on. So we can have an extended conversation across these three sort of time slots. And again, as I said, it's not, my goal is not here to cover all the slides or to go through all the slides, but just to sort of give you a sense of why these subsystems are important and exciting to begin with. I mean, just why is it interesting to do sort of, or just understand, then sort of do research in these general areas, right? So even before I get started, I just wanted to even just sort of abstract out 50,000 feet into a computer system. And as you might have sort of read in most of the textbooks or some computer organization course that you might have taken, a computer system today, especially the von Neumann models, essentially consists of three major components. One is your compute, which is your CPU right here. Then there is your memory, which is this one right here. And then the third component, the large component, is input-output systems. And I have just sort of chosen to represent this via hard disk drive over here, which essentially for one device or one closed box essentially remains the major or one of the two major kind of input-output subsystems that there is, right? So there are, if I look at it from the perspective of how programs are being executed in the life cycle of a program, assuming they're spread across these three major components of a computer system, you start out with a program as nothing that is essentially a binary that sits on the disk. It might be your C program that you might have compiled a little while ago, and then it's just sitting there on your disk in a file system. At some point in time, you decide that you want to run this program, and then you go into that directory. You do something like ./a.out or whatever the name of that directory is, or that executable is. Then a whole bunch of magic happens in the background where this compiled binary is taken and then kind of laid out into memory, right? And from this point onwards is when the execution of the program begins. And as a lot of you might know, the program that is laid out in memory is laid out in a specific format so that the computer system essentially knows where to start picking the instruction from, where the data for this particular program is located, so on and so forth, right? So this essentially is by and large, the life cycle of any program, right? I mean, I've taken the example of a compiled binary, but happens similarly in the case of interpreted ones where you write a Python programs and so on and so forth, right? So again, three major components. One is compute, the second one is memory, and the third one is storage. And each one of these play a role, right? I mean, if your program or the execution of a program consists of executing instructions on the data of a particular variety, then all of these things become important. All of these components become important. Your computer is important because it actually executes the instructions that you're trying to execute. Your memory is important because this is the place where your program or both the instructions as well as the data for that particular program is going to be laid out before it is carried over to the compute, whatever kind of compute. I've shown this as a CPU, but it could very well be a GPU, it could be an accelerator, whatever that is. But by and large, the mechanism of execution, program being laid out in memory, copied over to the or taken over to the CPU, where the actual number crunching is done and the final results are written to the memory, and then eventually they're written back onto the disk if need be. Right. So as you can see, all three components are important. A lot of the research that has been done in the previous years has been done around making sure that your compute, which is this CPU subsystem over here, is as fast as possible. It is able to crunch or execute as many instructions as possible in a given window of time. And that was mostly the focus for the largest amount of time in the history of computer systems, because the amount of data that these systems were processing was not very large. It was mostly a lot of these programs were mostly compute intensive, so it was necessary for everybody, or mostly computer system designers, to focus their attentions on how to make sure that they are able to compute or execute the largest number of instructions in a given window of time. But that has, as we'll see, has been changing over time, right? So now, given the fact that your data has to be laid out, or a program has to be laid out in memory and then brought over to the CPU, there is of course a latency difference between what your CPU can do and how quickly can you get your instructions and your data from memory, right? So if your core or your compute subsystem is super optimized, it can potentially execute, let's say, a simple instruction, one instruction every cycle or something of that sort, right? But that instruction has to come from somewhere in memory, which essentially is very far away in terms of time, right? So you are potentially, the computer is potentially capable of executing one instruction per cycle, but the time it takes to bring one instruction and the accompanying data that instruction has to sort of operate on from memory is of the order of 500 or more cycles, right? So if that is the case, then your memory system becomes kind of the bottleneck in terms of your overall program execution time, right? I mean, imagine that if you had to kind of go to memory to fetch one instruction, a 32-bit instruction or a 64-bit instruction, but it takes you 500 cycles to go to memory to get that instruction as well as the data associated with it, and then a cycle to execute that instruction. The majority of your time is being spent just going back and forth between CPU and memory, right? And that's clearly suboptimal. So one of the ways in which you would want to do speed up program execution is to make sure that this extreme latency of going to memory is sort of reduced, right? And people came up with a whole bunch of clever techniques, heart of which lies caching, right? So what you do is essentially, when you say, oh, this is my CPU, and rather than having to go off chip into memory, which costs me 500 cycle, I'll design this one entity called the cache. In today's process, multiple entities called the cache, which are going to store some of my instructions, some of my data, or typically the one that I am using right now, or I'm going to use in the near future over here, which I can access very, very quickly, right? And very quickly means somewhere between one cycle to, let's say, 50 cycles or something of that sort, right? I'm just making numbers over here, but it gives you a sense of why caches are important, because it cuts down your round trip time from 500 cycles to even 50 cycles, which is an order of magnitude win, right? So now that one instruction, which was executing in 501 cycles before, can now be executed in 51 cycles. And again, then over time, this concept has been kind of increased to give you multiple levels of caches and all kinds of innovations in the on-chip hierarchy, right? So again, as I said, multiple things have been done. People over time have found out multiple ways and different technologies by which you can access your data faster, right? So, for example, the fastest mode of accessing your data in a typical von Neumann machine is when your data is sitting in your registers, which is approximately, of the order of a cycle, which loosely translates to some nanoseconds these days, depending on how fast these processes are running. Right, and then you have on-chip cache hierarchies, which are made up of SRAM. Right, then again, there are few nanoseconds or few cycles to access those things. If you don't find the data or the instructions that you're looking for in one of these two things, which are essentially on chip or sitting right next to the CPU, then you have to go off chip into main memory, which is again couple of orders of magnitude higher latency. And even if you don't find your data or instructions over there, like the first time that you were trying to execute a binary that was sitting on the disk, and then it had to be brought into memory to be laid out before it can be executed, then you have to go to your tertiary storage subsystem, which is again multiple 5 to 7 orders of magnitude slower than going to DRAM, right? So again, considering the entire life cycle of a program, you have to start out with the disk, which is really, really slow. Try to make sure that most of what you're going to require from your program's execution sits in memory, which is a few orders of magnitude faster. And the next step is to make sure that whatever is sitting in memory is essentially brought onto chip, which is again a few orders of magnitude faster, so that everything, your data and your instructions, can keep pace with how quickly your CPU can actually crunch those instructions. Right. So again, the point that I'm trying to emphasize over here is the fact that a program's life cycle starts at the disk, goes to memory, goes to CPU, and sort of keeps going back and forth between CPU and memory for the most part, assuming that your entire working set size, which is all the instructions that you have and all the data that you have for a program, essentially fits in memory. Then you're just ping-ponging back and forth between the CPU and memory. But if that is not the case, which is the case typically for most programs today, which essentially is that your memory is sort of large enough, but it's not large enough to hold the entire working set of all the programs that are running on a given CPU, right? So as you know, all of the computers, most of the computers today are essentially multiplexing things, right? So right now, my laptop is running Teams, it's running Word, it's running a browser, it runs a few whole different things in the background, and all of these things require essentially memory capacity. And there, if my laptop is sort of resource limited, it can't keep all the data in memory. So then it has to keep going back and forth between disk and memory, which essentially slows down the execution of my program, right? So the entire goal is to make sure we feed our CPUs as fast as we potentially can from the least latency source of instructions as well as data. And the entire goal of this exercise is to make sure that we keep on decreasing the latency of each and every level that we have looked at so far, right? So you're trying to come up with memories or memory architectures that essentially have higher capacities and lower latency, so you don't have to go to disk as often. Then you keep designing storage subsystems. You go from HDDs to SSDs to so on and so forth, so that again, the same thing happens, right? You have larger capacities that you can access more amounts of data in as small latencies as possible. And essentially that is sort of like the design mantra over here, right? So then one can make the argument, right? I mean, okay, in the previous slide, I showed that, you have SRAM for the caches, then you have DRAM for the min memory, then you have, let's say, NAND flash for SSDs, and then you have just magnetic material for HDDs. Why not just make, something, or at least SRAM and or your caches and your memory of the same material, right? And this is what has kind of happened in the past few decades or so. Your on-chip caches have been made of what is known as SRAM, or static random access memory, and your off-chip main memory has been made up of a memory technology called DRAM, which is dynamic random access memory. And again, you might have tens to hundreds of megabytes of SRAM sitting on chip, and then you have multiple to hundreds of gigabytes of DRAM sitting off chip in DIMM form factors. So anybody wants to hazard a guess as to why we can't have, or we, let's say, don't want to have our main memory made up of SRAMs as well. Anybody who wants to speak up, feel free.
Very useful.
Sorry?
Consumes more area.
Okay, what else? I mean, SRAM is clearly faster, right?
System design is a bit more complicated for SRAMs.
Okay.
SRAM is volatile.
SRAM is volatile, DRAM is also volatile. So there is no clear winner there in terms of that particular metric. Anything else? Anything that you might be able to
number of transistors required, the transistor area.
Absolutely, right. So and it's a combination of these things, right? So this one right here gives you lot lower latency, but then it requires more transistors, right? More transistors means more energy being consumed, more area being required. This one over here requires actually just one transistor and one capacitor. So in a given square millimeter, let's say, you can fit a lot more bits. And assuming this one thing over here stores 1 bit and this one thing over here stores 1 bit, in a given square millimeter, you would be able to store more bits or more data using DRAM than with SRAM, right? So at the end of the day, it's all about essentially bang for your buck, right? So what you can potentially do is, for a given area, you can store a fewer number of bits at a much lower latency using SRAM. And for the same area, you can store a lot more bits, probably, approximately an order of magnitude higher and more if you can architect it very well using DRAM, right? So again, there are other complications that come along because of choosing DRAM over SRAM. But then again, at the end of the day, it's all about the value that it brings in, and then also the costs associated with it, right? I mean, manufacturing something that has 6 transistors as opposed to manufacturing something that has just 1 transistor is, of course, going to be more expensive, right? Not just in terms of energy that it's going to consume and the area that it's going to consume, but it actually in terms of dollar value, right? The same amount of SRAM that you could buy, or the same capacity of SRAM that you could buy in a DIMM form factor, is going to be multiple orders of magnitude more expensive, right? So you can't just go out, or you would have to think twice, let's say, before going out and buying your main memory that was made up of just SRAMs, right? So at the end of the day, it's a complex optimization function in which you're trying to optimize for latency, you're trying to optimize for capacity, you're also trying to optimize, at least the industry is trying to optimize and make sure that it is at a price point where people are actually willing to pay something for that product, and not something that's gonna just goes out of use really quickly, right? So anyways, the problem, like we talked about with SRAM caches, is that they consume more energy, they consume more area, but they're also much faster. So you can't completely do away with SRAM completely, right? Because there's again at least 1 to 2 orders of magnitude lower latency with SRAM as compared to DRAM. So you can't completely get away with SRAM. And as you move from, so I'm just going to write this down over here, SRAM to DRAM to, flash or something of that sort. As you go from right to left in this diagram over here, you experience much lower latencies, and where you ideally want to be is essentially at SRAM-like latencies, right? So again, lower latencies, higher energy, but then again, you want to make sure that you sort of architect something that uses maybe a combination of all of these things, but as far as the program is concerned, just because of intelligent management of data across these different memory technologies being used at different levels in a computer system, essentially gives the program the illusion that whatever data that it requires, or instructions that it requires at some point in time, is available to it at SRAM-like latencies. Let's put it that way. And how you manage that is essentially the intelligent design that goes along with it, right? So, anyways, you can't have more than a given amount of SRAM on your CPU just because it consumes area, it consumes energy, and at some point in time, your CPU is going to be super hot that it's going to probably melt down. So you don't want that either. So you have to shift to different technologies, right? So DRAM, off-chip DRAM, has been the mainstay as the main memory for a very long time. And over time, the applications have also been changing, right? Applications have changed to use more instructions, which again translates into a larger memory footprint. They are working on larger and larger sets of data, which essentially, as we saw before, needs to be kept in memory, right? So all of these things, and then a given system is also sort of using or executing multiple programs at the same time, right? So if one program wanted 2 gigabytes of total capacity to execute properly, 10 programs now require 20 gigabytes. I mean, just as an order of or a rule of thumb, right? So you want increasing capacities for your main memory over time goes, and of course nobody wants to pay higher prices for that, right? So you want your prices to remain constant, but you want higher capacities with hopefully better latencies for your memory subsystems as well, and which was very much possible as and when transistors kept on scaling and people or DRAM designers were able to sort of put in a large number of bits or pack in a large number of bits in the same square millimeter over time, but that has also kind of slowed down over time, right? So as you can see over here, the amount of capacity that you can pack in one DRAM chip has not been increasing at approximately the same pace as the programs have been adding the capacity that they require. So at some point in time, you're like, well, okay, DRAM is good in terms of the latency that it provides me, but I need more capacity with DRAM-like latencies for something at the level of main memory, right? And that essentially is the primary sort of driving factor behind why people have started looking at non-volatile memories over time, right? So again, I'll not go into what are the other problems with DRAM also, right? So for example, DRAM is dynamic random access memory, and the reason it's dynamic is because it requires sort of refresh over time. So information in DRAM is stored as a charge in a capacitor, which you can sort of think about as a leaky bucket, right? So you fill the water into a bucket, but there is a hole in the bucket. So over time, essentially the charge leaks, which essentially means from an information perspective that bit has flipped, right? If enough charge has leaked, then that bit has flipped. And the smaller your capacitors get, which you have to do when you're trying to pack in more capacity in given square millimeters, the faster it is that the charge leaks, and the more frequently you have to refresh that capacitor. Sorry, there is some sort of background noise there. If anybody is not muted, can you please mute it? Excellent. Right. So we've talked about, okay, how DRAM has been the mainstay of main memory over time. And there are various problems with DRAM. Capacity has not been increasing at the pace that we want. As you pack in more density, you have to refresh more frequently, which again is not a very good thing. You have to do it because the technology or the cell requires it. But from the program's perspective or from the system's perspective, DRAM refresh is just overhead, right? You have to do it because you want to make sure that your information or the sanity of your information is actually maintained. But while you're trying to refresh information in there, you can't actually use DRAM, right? I mean, so imagine you're trying to refill the bucket, and you can only start using water from the bucket when it has been completely filled up. You cannot sort of use the water while the bucket is being filled up, right? So from a program's perspective, while DRAM information is being refreshed, for that portion of DRAM, things are just stalled. You can't access or you can't read that portion of that DRAM over there, right? And as I mentioned previously, not only have the requirements of individual programs in terms of memory capacity and latency been increasing, but more and more new types of workloads are coming up, right? So I don't know if you've heard of these names. I mean, of course, I'm pretty sure everybody's heard of this. But there are a lot of workloads or applications that are coming up that are sort of running on large data sets, right? So you have in-memory computational frameworks, right? I mean, these are different from in-memory architectures, in which the idea is you can bring all your data into memory, you let's say never have to go to disk, and then the application itself picks the data from memory and then make sure that it never has to go to disk, right? So all of these different types of workloads have been coming up, which have a larger footprint in terms of both the instructions as well as the data, which eventually translates into all of them requiring larger and larger memory capacities at fixed energy as well as better latency budgets, right? I'll give two quick examples from the handheld sort of domain, right? So in this particular slide, you have different browsers over here, and the amount of memory capacity that they're required to do two things on the x-axis, right? So this is megabytes. Again, take this with a grain of salt, but again, it's supposed to be representative, right? The blue bars are when they have to sort of open up one tab, but nothing is loaded. And then the cumulative orange bars, or the blue plus orange bars, are the ones when you have 5 tabs open and 5 different web pages open in this. And as you can imagine, even in this, and this is something which is from a few years ago, some of the browsers end up using as much as 500 to 600 megabytes of memory on a mobile subsystem, which are essentially optimized for all of these things. Of just capacity. Now multiply that with sort of 20 programs that you might be running in parallel. And then as you move from mobiles to desktops to servers, this requirement, the memory capacity requirement from a per program perspective kind of keeps on increasing, right? And essentially this is again trying to show the exact same thing. I'll give you a couple more of these points in terms of why it is important to optimize the memory subsystem from an energy perspective as well, right? So if you look at where the energy is being spent in servers, approximately a quarter of the energy is being spent in memory, and this is a function of more memory capacity that is associated with the system, as well as more refreshes that have to be done over time to make sure that the sanity of data is preserved. A quarter of your energy is being spent just trying to maintain your information in memory. And then again, as you see in different types of computational devices, somewhere between 20 to 25% is essentially being spent, or 20 to 35 or 33% is essentially being spent in memory energy, right? So the total energy of the system, a third of that is essentially being spent in memory. So again, it's not just the compute that's taking up all energy requirements, but it's a significant fraction of it also goes towards DRAM, right? So now we have multiple problems. We have with DRAM specifically as a memory technology, is something that it's not scaling very well. It's something that is consuming up a lot of energy, right? And the only benefit that we have going for it so far is that it is the next best thing to SRAM in terms of latency, right? Anything else, any other memory technology that you consider so far is very far removed from SRAM in terms of latency. But again, all of this calls for optimizations that are required for this for this subsystem, right? So again, as I said, all these applications are trying to consume as much memory capacity as you can potentially provide them, and this is something that you'll see with the new set of or the next generation applications that are coming up as well, right? So what do we do about this? I've sort of enumerated all the problems that are there potentially with DRAM, but then how do we kind of go from what we have today to something that essentially is, let's say, better or tries to handle at least some of the problems that I have identified so far, which is an increased energy consumption, not fast enough increase in terms of capacity being generated, and something that is not scaling really well, right? 10 years ago, people were saying that the DRAM is not going to scale beyond 40 nanometers. That is not true today. But at some point in time, you're going to run into the laws of physics, and then things are not going to scale very well. So we need to move on to things, or to move on to technologies that just scale a little better. And that is where this newfound interest in memory technologies in the past, or non-volatile memory technology in the past decade, right? So there's nothing sort of very new fundamentally about non-volatile memory technologies. They've just been around for very long. They've been around since the 60s. It's just that people have started to feel the need of exploring these more in the past decade or so. There are multiple of these technologies around. So we've talked about few that have traditionally been used. We've talked about SRAM, we've talked about DRAM. Now, there are other technology types, for example, phase change memory, spin torque transfer memory, 3D crosspoint, which we'll talk about a little bit more, resistive RAM. All of these technologies are ways in which you can store information. And they can potentially be used as replacement for DRAM, and replacement I say with a pinch of salt right now, right? The primary difference between all of these technologies that I have kind of encapsulated over here between DRAM and SRAM is one, they're non-volatile, and two is the mechanism by which they store information, specifically with regards to or with regards to DRAM, let's say, right? So if you remember, what I talked about in DRAM was DRAM stores information as charge on a capacitor, whereas most of the other things, most of the non-volatile technologies that I have mentioned so far are essentially things that store information as resistance, right? So what do I mean by that? So I'll just take one quick example of something which is known as phase change memory, which is made up of what is known as a chalcogenide material. So if you look at this one cell over here, it has this layer right here, which is made up of a chalcogenide material. And this material's state can be changed from amorphous to crystalline by the application of a specific current pulse for a specific duration, right? And let's not go into details of how much current and for how long is required to be passed through this. But what is important to note here is that there is one material, which is this chalcogenide material over here, that can be stored in either the amorphous or the crystalline shape or a crystalline form, and you can go interchangeably between the two states. The crystalline state has low resistance, so you can potentially associate that state with, let's say, the logical value 0. And amorphous, which has a high crystal or high resistance state, you can store with the value 1, and then you can differentiate between which state this particular layer is in by trying to sense how much current sort of passes through this cell, right? So if a large amount of current can pass, then of course this material is in the crystalline state, and then you know what value is being stored in the cell. And if little amount of current passes, then you have more resistance, and then it's in the amorphous state, and that's and that's different sort of logical value associated with it, right? So again, this is essentially the crux of the matter that I have described so far. So rather than encoding information as whether the capacitor is full for a 1 and the capacitor is empty for a 0, we store information as whether the resistance of the material is high for a 1 or low for a 0, or however it is that you want to kind of store it, right? But that's sort of like the crux of where these technologies come into play, right? So that's one fundamental difference in terms of how they store information. Again, different technologies store information in different ways, mostly in terms of resistance. So for example, memristors, RRAM or RERAM essentially store information as resistance, but the amount of resistance is defined by the change in atomic structure, and the resistance, or rather the resistance is determined by how much distance is there between the atoms. Some other technologies like STT-RAM essentially store information as again resistance, but that resistance is determined by whether two layers of the material that are encoded within a cell, which is known as the free layer and the other one is the fixed layer, are in parallel or anti-parallel state, right? So if they are in anti-parallel state, then it is a high resistance state, and then this cell can be associated with a particular value, say 1. And if these are in a parallel state, then the cell is in a low resistance state, and then the information associated with the cell can be 0, so on and so forth, right? So again, there are multiple types of these technologies, and at the cell level, they store information a little differently than DRAM does, right? The non-volatile sort of part of it is just incidental to some extent, right? I mean, they're non-volatile. This is not something that people were explicitly looking for. What people were explicitly looking for was something that is higher capacity and lower latency. But this non-volatility just came in as a side effect, right? So how does this give us increased capacity? Let's say we are into um, cells that can help us store information as resistance. How does this help us increase capacity? So let's say I have one cell which has a resistance range of this many, let's say, ohms, right? I can split that resistance range into two particular regions. Let's call this the region 0 and I'll call this the region 1. And if I program my cell in this region of resistance range, then the value associated with the cell is 0. If I program it over here, the value stored is a 1. Now I can take that same resistance range and break it down into multiple resistance ranges, and I can store multiple bits of information with each one of these ranges of resistance, right? And again, as you can imagine, I can sort of keep breaking these down into even smaller ranges, and that again is a function of how well the circuit designers are able to provide circuits that can potentially be programmed in a very small resistance range, right? So given a resistance range for particular memory technologies, if I'm able to program it into with large confidence, and I think that's the key here, with large confidence in this smaller range, then I can have more and more capacity per cell. So even with one cell, I can keep adding more bits of information, right? I can go from 1 bit to 2 bit to 3 bit, so on and so forth. Right, and this is also and one of the promising features of most of these technologies is the fact that you are able to potentially do that with decreased or as and when the technology scales as well, right? So okay, so I'll quickly stop here and see if there are any questions. Otherwise, I'll move on. Okay. All right. So most of these things I've kind of talked about over here. The good thing is, again, as is with the design of any sort of subsystem within the compute systems, there are always good and bad things, right? So you have to manage the positives against the negatives. The positives over here are there are many sort of candidates for these non-volatile memory technologies. They have higher density, same square millimeter. I can pack a lot more bits, like I showed before. And then, of course, just because they are non-volatile, I don't have to refresh them. When I write into one bit, it's there until something bad really happens, right? But then again, there are negatives over here. Nothing comes for free. They have higher access latencies, asymmetric read and write energy, which essentially means that as opposed to DRAM, where both reads and writes essentially cost the same amount of energy as well as latency, in most of these technologies, because of the amount and duration of the pulse of the electrical pulse that needs to be required to change the state, for example, in phase change memory, is different. You have to have, or you will have, asymmetric read and write energies as well as asymmetric read and write latencies. If you're trying to write to a cell, it's going to take longer, whereas if you're trying to read from a cell, it's going to take shorter. And the hope is that over time, these will sort of converge together and they will become small enough for it to not matter, but at least so far, that is not the case. The biggest problem with most of these technologies is that they have limited lifetime. Again, going back to the example of phase change memory, you are passing amounts of current and changing the state of the chalcogenide material over time, right? And the more number of times you change the state, or let me put it this way, there are only so many times that you can go back and forth between amorphous and crystalline to the point where you cannot do it anymore, right? So to a certain extent, that state or that cell cannot be flipped from crystalline to amorphous or the other way around. And from that point onwards, that cell has become useless for all practical purposes, right? And this is something that has to be considered when you are designing memories based on these non-volatile memory technologies, right? So again, you have got things. You have higher densities. You have no refresh energy. You have something that scales very well, but then you also have these kind of drawbacks, which essentially is sometimes more energy or asymmetries in terms of read and write energies, asymmetry in terms of read and write latencies, and also the latencies are sort of still quite far removed from what you would expect the latency of a main memory component to be, right? So they are not quite there as DRAM write latencies as we would expect them to be, right? So the question then becomes is that, well, okay, we have these good things that are coming from these memory technologies that we have found out, but they're not quite there yet in terms of latency. So what do we do? And the question, like when we had the choice between SRAM and DRAM, was, well, use a little bit of SRAM and use a lot of DRAM, because then you have to balance out the latency requirements with capacity requirements with energy requirements, and that's the exact same sort of trade-off analysis that we can now apply over here as well, right? So we use the pluses of these non-volatile memory technologies and use whatever else that we have available to us to be used at that level in the memory hierarchy, which is DRAM, specifically for main memory, to overcome the minuses, which is mostly in terms of latency. And so how do we actually go about architecting something which is useful and is able to leverage kind of the best of the both worlds, right? So the two main kind of design points that have been propagated by most research that's been done in these areas is essentially what is known as a single address space variant, in which you have a large physical address space that is split between a low latency variant, for example, in this case, DRAM, and a high latency, but also high capacity variant, which is some sort of a non-volatile memory. It could be phase change memory, it could be STT-RAM, whatever else you might have. And then you split your information in main memory accordingly between these two areas, right? So for example, your hard data goes into DRAM and your not so hard data goes into the non-volatile memory. And some entity somewhere is responsible for managing this placement of data between these two sort of split address spaces to some extent, right? So for example, your memory controller, which sits on the CPU right here, might be aware of that, out of whatever gigabytes of physical memory address space that we have, some amount is dedicated to DRAM, and this is what the address range for that is, and the rest of it is for NVM, and the address range for that is that, and I will manage or map data accordingly to these address spaces, depending on what the requirements of that data are, right? So somebody has to externally, and this could also be done at the operating system level, but then again, somebody has to sort of manage that externally. The other variant, which is a more sort of hardware managed, by and large hardware managed variant, is what is known as a DRAM as a cache, right? So in the DRAM as a cache variant, it's relatively straightforward. You again have both DRAM and NVM. The address space that is visible to the CPU is that of the NVM, so that is the entire physical address space. But there is also some amount of DRAM that is present, which serves as the cache of whatever data that is actually sitting in the non-volatile main memory. And this caching of data in DRAM, or caching of NVM data in DRAM, is essentially maintained transparently from the application's perspective, or even from the system software's perspective, right? So the operating system doesn't have to explicitly manage data between the NVM and the DRAM in this particular case. It is managed explicitly by the memory controller that is sort of sitting on the CPU, right? And both of these variants are present in today's, well, basically the only product that's available on the market for non-volatile memory as such. So Intel Optane or Intel's Optane line of products are the only products that are available today, and they have again the two sort of modes that I just talked about, and they of course call it differently. One is called the memory mode, in which the DRAM, which sits over here, is used as a cache of this Optane DIMM, which I was calling NVM in the previous slide, right? And then the other one is called the app direct mode, which is the single address space variant, in which this DRAM over here and this obtained DIMM over here are essentially one large address space. And of course, there are multiple sort of changes or there are changes that are required at multiple levels to bring this to fruition, right? So the biggest change that needs to be done is to make sure that this IMC, or the integrated memory controller, as it is called, is able to kind of or is actually cognizant of the fact that there are two types of memory technologies that are sitting on this channel over here, which is both DRAM as well as NVM, and it is able to talk to both of them accordingly. Right, and that essentially requires that you need to move away from the standard protocol that you used to talk to DRAM DIMMs, which was, the DDRX 3, 4 kind of protocols that we've been sort of used to seeing for a while. And that has moved to which is known as a DDRT protocol, right? So again, there's a lot more detail that that can be talked about in terms of what the architecture of the Optane looks like internally, and I'd be happy to talk about it at later time. But what I also wanted to give you a sense of is what else can be done with these non-volatile memory technologies, right? So far we have talked about how you can take a non-volatile memory technology and kind of apply that into or to create a memory architecture or a hybrid memory architecture by and large, so that you can get the best out of both worlds in terms of latency as well as in terms of capacity. But then, are there possibilities in which these non-volatile memory technologies can be moved even closer to the CPU, right? I mean, eventually the goal is to make sure that you have the largest amount of data instructions possible at or as close to the CPU as possible, so that they can be accessed with the least latency possible, right? And all of these optimizations that we're doing with architecture are one way of doing that. So we can do that at the memory subsystem, or we can try and do that at the cache subsystem, right? So again, you would potentially get more benefits at the level of the caches, because they typically sit right next to the CPU on chip, so you don't have to cross over from being on chip to off chip and then coming back again, which is going to help you reduce your latencies even further, right? But the problem then becomes is the fact that there has to be some compatibility in terms of the fabrication process, right? I mean, one of the reasons why SRAM has been incorporated so easily into on-chip CPUs is because the fabrication process that go into making, let's say, the pipeline are essentially very compatible with designing SRAM caches. That might not be the case with something like STT-RAM or phase change memory that comes along, which might bring in their own set of challenges, right? But that being said, assuming the hypothetical case that, let's say, at some later point in time, that is actually feasible. Let's say there is feasibility in terms of being able to fabricate an STT MRAM entity sitting right next to an SRAM entity. Then what are the kind of optimizations that we can potentially do to make sure that we have on-chip caches that have large capacity and lower latencies? And the idea over there is also very similar to the high-level ideas that we just talked about in terms of a main memory, where we were playing with DRAM and some NVM. And in this case, when we try to bring the optimizations onto on-chip caches, what we're trying to do is we are just playing with SRAM and some NVM. And that definition of some NVM or the choice of that some NVM is going to be dependent on a whole bunch of other factors: compatibility, energy, latency, so on and so forth, right? But then again, the kind of optimizations at a very high level that you can potentially do are very similar to what we have talked about, right? So for example, what you can do is you can have, and again, this is all on chip, right? So you could potentially have an SRAM L1 and an STT RAM L2, again, assuming manufacturing compatibility. You can have L1 SRAM, and then you can have L2, which is made up of some amount of SRAM, which is right here, and some amount of STT RAM right here, right? So overall, this level, this L2 level, has a much higher capacity as compared to right here, right? But it also might have higher latency because STT RAM might have higher latency than SRAM, right? And then again, of course, then you can go all the way and completely sort of have STT RAM that is removed off chip and then is subject to the same set of optimizations like we talked about previously, right? So again, one of the things that I sort of wanted to bring about in this particular slide was the fact that uh, your optimizations at a very abstract level, the kind of optimizations that are possible, remain very similar in terms of the different levels of the hierarchy, right? It's just that the choice of variables that are associated with each one of these different kinds of technologies changes, and the kind of optimizations that you have to do, or your optimization function for designing a cache or a non-chip cache, which is a hybrid of SRAM and some other NVM, is different from the objective function that you might choose in designing a main memory technology that is sitting off chip, which is a combination of DRAM and some NVM, whatever be the flavor of the month, right? So one of the or large takeaways that I would sort of try and put out from this part of the lecture, and I think I'm kind of out of time, so that is essentially very good because then I don't have to go into storage. So two things, right? I mean, a lot of the architectural optimizations that are being done are many times driven by the needs of the applications and how many what kind of applications you're co-locating on a similar machine, right? On a server system, if you're co-locating applications that require a lot of memory, then you of course need more capacity, more number of channels so that you're able to connect more DIMMs and so on and so forth. But the primary sort of metrics that remain to be or that remain unchanged in terms of things that need to be optimized are: one, you need higher capacity at all levels. Again, the objective function of what or the definition of what constitutes higher capacity is going to change depending on the level. You need lower latency, right? And then you of course need lower energy consumption at all levels, right? So these are at a very high level the kind of optimizations that you need to do at every level of the memory hierarchy. And to some extent, NVMs are or allow you to sort of play around with these different or trying to optimize these various metrics at various levels of your memory hierarchy as well, right? So again, as I said, architecting any computer system or any subsystem of a computer system is essentially a trade-off analysis, right? You want to get something out of it. So if you want to get something, you have to give something, right? And what we want to do in this particular case is these are the things that we want to optimize. And then again, NVMs gives you one more knob in conjunction with whatever else you have available to make sure that you're able to kind of do a better job at designing these subsystems. Okay, so so at this point, I'll just quickly stop and take whatever questions that you guys might have. I'm already out of time, unfortunately.
Manu, you can go until 11:30.
Oh, is
You're
it?
out of time. Yeah.
Oh, I thought it was only 11:15. Okay, never mind. In that case.
You started at 10:15.
Okay. Okay. Any questions so far on this? No? Okay. All right. So let's see what else can we potentially talk about. So let me just whoops. I'll just quickly talk a little bit about storage systems as well, and I'll just go into the SSD component of it, right? And that sort of brings me back again to this original diagram of a computer system that we had. We are trying to, or what we had looked at so far, at least in the previous section of the talk, was we have on-chip caches over here, and we have the main memory over here. The entire goal of the exercise is to make sure that we have as much data and as much instructions that we need over here. I mean, ideally, we would want 100% of all our instructions and all our data to be here, but that's of course not possible given our energy constraints, given the amount of money we are willing to pay for a given processor as well. So the next best thing is at the memory level, and then we saw multiple optimizations that can be done over here. For most programs that have very large working sets, which essentially means that they are processing a large amount of data, let's say terabytes of data, these genomics applications, which essentially have, you have your genomes mapped out, and what they're looking for is basic, or what they're essentially running are some sort of string matching algorithms across a very large data set, right? And of course, you have only, let's say, a typical server system might have only 32 GB or 64 GB of memory capacity, and you're running on genome sequence that is 1 terabytes, right? And just to pick an example, and there are multiples of applications like this. There is no way your entire 1 terabyte is going to fit in into this over here, right? So what you'll eventually have to do is you have to bring in some chunk of your data into memory, process that thing, throw it out, and then bring in the next thing, then bring the next chunk, so on and so forth, right? So you this is essentially what you do. You bring in data from here to here. This is step one, right? You map it out over here. This is step two. And then you bring it over here in step three to process it, which is then stored over here, and which is then eventually stored over here in step 4 and 5. Let's forget step 4 and 5. Let's just concentrate on steps 1, 2, and even just 1 and 2, right? I mean, let's forget 3, 4, and 5. If I have to process such a large data set, I have to do so many round trips from my storage subsystem, which is right here, to my main memory, just trying to bring in, let's say, 32 gigabytes of data at a time out of a 1 terabyte data set. This is accessing memory is of the order of nanoseconds. Let's also be very optimistic in terms of what kind of latency our memory system can provide us, and let's say it is best in class DRAM-like latency, right? Whereas if I had a regular storage subsystem, this latency of this system right here is of the order of milliseconds, right? So that is multiple orders of magnitude, which is 6 orders of magnitude, and 6 orders of magnitude higher latency just to fetch data from this level over here, right? And this is something that I have to do. I cannot escape it because that is where the bulk of my data resides, just because of how large the data that I'm working with, right? So just bringing the data back and forth between storage subsystem or the storage subsystem and the memory is going to cost me a lot of time. And that is something that I want to avoid, right? I mean, that is the eventual goal of your storage subsystem optimization, right? So and again, there are economic factors at play over here as well. You want to, again, I mean, the similar sort of arguments apply here as well. You want to store as much data as possible. You want to pay as little for it as possible, and you want to have as again lower latency for this as possible as well, right? So what has happened in the past, which essentially or what has been the mainstay of our storage subsystem has what has been known as a hard disk drive, right? And again, hard disk drives have different architecture as opposed to the DRAM or the SRAM or the non-volatile memory architectures that we have seen before. And I'll just quickly discuss that, and also that will also give you a sense of why there is this multiple order of magnitude difference in terms of latency for the hard disk drive versus the main memory. right? So information in hard disk drives is stored on what are known as magnetic platters. Platters are nothing but disks that have magnetic material sort of coated on both sides of them. And information is stored on these magnetic platters in concentric circles, right? So you have information being stored over here and so on and so forth. Each one of these concentric circles is what is known as a track, right? And each one of these tracks, so you can think about this cylinder or this disc as a pizza, and then you can sort of slice out the pizza into sectors, right? And wherever this slice of the pizza intersects with the track is what is known as a sector, right? So, and the basic unit of information storage on a hard disk drive is what is known as a sector, right? So, and these are typically, let's say, 512 bytes in size. So if I wanted to store some information, or let's say I want to retrieve some information, what I want to do is I want to give the hard disk drive a sort of a platter number. So I have multiple platters over here. This is platter number 0, this is 1, this is 2, this is 3. Then I would say, okay, go to platter number 0, go to track number so and go to sector number so on that particular track and fetch out that information, right? And this is how I typically access that information sitting on my desk. Now, in order to be able to get to a particular track or to get to a particular sector, I need to be, I need something that can sort of traverse back and forth across all of these concentric circles or track, right? And that job is being done by this black thing over here, which is known as the magnetic head, right? It sits on an actuator arm, right? So this is the arm. This thing is fixed. And all it can do is kind of rotate on this fixed axis like this. And that way it is able to traverse the entire radius of this platter so that it can go to any sector on any track, right? This head over here has a unit that is fixed on top of it. And this unit is able to read out the information from any given sector. Once it has reached to that sector, by using electronic circuitry, right? So again, to get information out of any given place on a hard disk drive, what you need to do is one, to make sure that your actuator arm essentially goes to the right track, right? This is what is known as the seek latency, right? So you have to move the motor so that it goes onto the right track. Then all of these disks are actually spinning at a fixed RPM, right? To get to a given sector that you want to read the information out of, you have to wait for a little bit for the disk to rotate enough such that the sector that you want to read is right beneath this particular arm. That is what is known as the rotational latency, right? And then once the sector is right beneath you, you suck out the information from it, and that is what is known as a transfer time. So these are the three main components that are required for you to read data out of a given sort of location on your hard disk drive, right? And as you can imagine, because this involves mechanical moving parts, right? You have to move the arm to the right track. Then you have to wait for the right sector to come under the head, and then you have to suck information out of that track, which is the transfer time. All of these things are super slow as compared to your main memory, and super slow as compared to how fast your CPU can actually process things, right? And that's one of the reasons why hard disk drives are multiple orders of magnitude slower than even your DRAMs, because they involve mechanical moving parts, right? And that's also because of the presence of mechanical moving parts is also one of the large causes of failure of hard disk drives, right? So you might have heard about typical failure situations in HDDs where they said that your head has, or your hard disk drive has crashed, right? When they say your HDD has crashed, what they actually meant was that the head that sits right here is essentially something that has crashed into your platter over here so that it cannot move back and forth without scratching it and destroying the information on your platter, right? And that's where crashing of the hard drive found its origins. Anyways, so this has typically been the mainstay of
Is
most of
the
our storage.
reason we don't have multiple heads to reduce the rotational latency because it keeps crashing?
So again, that's a good question. We do have multiple heads. To increase the storage capacity of a hard disk drive, there are two ways. One is you can increase the information that you store on one platter. The second way is you can have multiple platters, right? So you can have 4 of these platters, so your capacity becomes 4 times as much, right? So when you have 4 platters, then to read information out of each one of those 4 platters, you need 4 heads on each one of these platters. What you typically don't have is essentially multiple heads on the same platter that are moving, in different directions, which essentially increases and that's a valid design point, right? I mean, you could potentially argue that that is something that we should do, and people did that in the past. And what they found out was that just because of so much movement, again, these disks are spinning at a very high RPM, 15,000 or so RPM, and then these arms are not actually touching the disk, they're actually floating on the disk with a very thin layer of air between the head and the platter, right? So it's a very delicately balanced system, and the more noise you introduce into it by multiple sort of arms moving on the same platter, the higher your chances are that one of them is going to crash into the platter, right? So
Right.
to answer the question, there are multiple sort of heads, but they are not on the same platter. There's one head per platter, and then you might potentially have one head per side of the platter, right? I mean, because there's no reason why you can't store information on both sides of the platter if you can coat it with magnetic material, but never. But let me sort of qualify that. We don't have a successfully working design in which you have multiple heads on one side of one platter. That makes sense?
Yeah, right.
Cool. Okay, so this is essentially, in a nutshell, what disks are all about, right? And one of the reasons why disks have stayed relevant for so long is because even though they have terrible latency, we have been able to keep the price per gigabyte, or not we, but the industry as such, has been able to keep the price per gigabyte ridiculously low, right? So the amount of rupees that you have to pay per gigabyte has been just steadily going down over time, and that's one of the reasons why disks are kind of still around. That's point one. Secondly, not every application has the requirement of super high latency, right? So let's say I'm running some batch job and I'm completely fine with it if it takes, a month to finish. These are the kind of applications that could very well be run on just using hard disk drives. So we don't have to kind of move to a faster medium. But there are, again, applications that require faster storage subsystems. For example, things that require, let's say, real-time analytics. If you want to do real-time analytics, you want to read all the data out very, very quickly. And for that, you kind of need a better medium, which is your SSD, right? SSDs are, again, solid state devices. They don't have mechanical moving parts like hard disk drives do. They are made up of the primary storage technology, or the prime cell is essentially what is known as a NAND flash. Again, this is something which is technically a non-volatile memory technology. It has been around for the longest amount of time, but it's only in the last 15 or so years that SSDs have actually been used as viable and somewhat economical storage alternatives. And that has, again, to do more with economics than technology itself, right? So if you look at how price per gigabyte has changed over time, this is the price per gigabyte of hard disk drives, the red curve, and the yellow curve is the price per gigabyte of SSDs. And they only very recently, as around 2009 and 2010, is when they have sort of converged, just because the volumes were large enough such that people or the manufacturers were okay charging smaller margin per unit. And that's the time frame when sort of SSDs kind of became mainstream. So nothing sort of very new with the technology. It's been around for 60, 70 years. It's just that the economics of it sort of started making sense 15 years ago, right? So since I have 5 more minutes, I'll just quickly go over the architecture of an SSD. Like I said, the modern SSD's primary storage component is what is known as the NAND flash cell. Again, as is with any sort of storage or memory technology, it has its own set of peculiarities. And to sort of overcome those peculiarities, the SSDs have been architected a certain way. So what are the peculiarities of NAND flash? The first one is if you want to write a 0, if the cell is a 1, you can write a 0 to it relatively easily. But in order, so every NAND cell can be set to 0 individually, assuming that it was, or rather, let me put it this way. If the cell was in a set state, which is 1, it can be changed to 0 relatively easily. But the other way around, a group of cells have to be sort of reset or reprogrammed, right? So an entire group of cells need to be reset. So this is essentially what is known as an erase operation for NAND flash, right? So again, if you want to set a cell from 1 to 0, individual cells can be done, but an entire group of cells, which is essentially typically at the level of block, needs to be erased or programmed so that you can sort of change it to some other value, right? And based on this particular peculiarity of NAND flash is how SSDs today are essentially designed, right? So you have a whole bunch of these cells that come together to make an array. So you have an n cross n array of NAND devices, right? And a bunch of these arrays make up what is known as a page, and a bunch of these pages make up what is known as a block. Again, this is not to scale. It doesn't show the correct circuitry. I just wanted to give a logical impression of how things are arranged, right? In order to be, again, one of the things that you have to remember is that in order for, there is no in place write that can happen right away, right? So in an HDD, if you wanted to change a particular bit from 1 to a 0 or the other way around, you can actually go to that bit and change it, right? Whereas in the case of SSDs, you can't go and change that bit which was a 0 to a 1. You have to first sort of do the erase operation and then change that particular bit, right? Which adds to the complexity of the number of things that you have to do before you can do an actual update to a particular cell, right? So again, what you essentially end up doing is you take a block of, and erase is a costly operation, right? I mean, resetting a bunch of cells is a costly operation. So what the device has been architected to do is to make sure that you erase a large group of cells in one go so that all of them are actually ready to be written, right? And that's why erasers are done at the level of a block, which is essentially a collection of pages. Whereas individual read operations can be done at the level of pages, right? So this is essentially the differences that you need to keep in mind. And one of the black sort of chips, NAND flash chips that you see is made up of a whole bunch of these blocks, right? So you can think of, visualize a black NAND chip consisting of a large number of blocks. Each one of these blocks can be erased or has to be erased in one go. Each one of these blocks contains a number of pages which can be read individually. One of the peculiarities of NAND flash is that there are no in-place updates. You have to sort of write to a different location. So this is how typically SSD is architected, right? So this is one of those black flash chips that you might see over there. It consists of a large number of blocks, which again has the same logical architecture like we talked about in the previous slide. You potentially have a large number of channels from which a number of these flash memory packages can be hanging, right? You have one of these controllers that is able to talk to a particular flash module and go to the right place where you need to retrieve your information from, right? And so this subsystem, this particular subsystem in this box is responsible for managing the flash devices right here, right? This larger box, which is called the Ssd controller, is something that takes in a request that comes from an application. Let's say the application says, go read me /home/foo.txt. That is something that is sent to the Ssd controller, which figures out sort of to some extent where that particular piece of information is located. So in an HTD, that foo.txt or the part of foo.txt that you actually want to read might be sitting on some platter, some track, some sector, and that's the information you need to sort of convert or retrieve that information. Whereas in this particular case, in the case of an SSD, that foo.txt or the piece of foo.txt that you want would be sitting on some channel, some flash chip on that channel, some block, some page, and some array within that channel, right? So again, there are multiple level of indirections that you have to kind of traverse through to be able to retrieve the information that you want. The biggest benefit of SSDs over HDDs is the fact that there are no mechanical moving parts. So there is no, no motor, no actuator arm, no spinning disks, nothing of that sort. So technically, all of this can be done at how quickly the electrons can kind of move through the system, which reduces the latency of accessing a piece of information from the SSD by multiple orders of magnitude as compared to the hard disk drive, right? And again, you have to sort of keep into account a number of peculiarities of how or what NAND flash requires, so that you can, make sure that your device lasts longer, your latencies are kept in control, and so on and so forth. But that essentially is at a very high level the architecture of an SSD. And let me just stop right here because I'm kind of out of time. But I'll stop here and take any questions that you might have. All right. If there are any questions, I'll be around for the afternoon session as well as in the doubt clearing session in the evening. So let me know.
Right. Thanks, Manu. For the lab session, just a reminder, you have already posted the
Yes.
requirements in the channel, right?